So the topic as we are going to dissect today is the interface is still the device. It's a very important topic. And when we talk about device, we talk about a lot of things now, the photovoltaics and the batteries and everything that we are interested in to drive the green energy economy are going to be based on devices to convert those energies. And these are driven by a lot of interfacial phenomena, and therefore the interface is still the device. So our goal is to engineer them so that we can improve their performance. Today, I will be more focused on thin film solar cells, but this is still relevant to a wide range of other technologies within the green economy. So for those who might want to pick up some interest in our research activities, so forming strands cut across thin film photovoltaics is one of the key areas we are really driving within my research group, the materials and mineral theory group, where we really want to understand what is happening at interfaces, what are the bottlenecks that we need to fix in order to drive performances of devices that we fabricate from those materials. We're also heavily driven by heterogeneous catalysis. My PhD has been strongly in catalysis, so we have very strong expertise in modeling chemical reactions and understanding what mechanisms drive particular reactions towards a particular product. And those are things that we are interested in. Within the battery technology as well, we are really interested. A lot of interfacial phenomena happen there, and we really want to understand them. Particularly currently within the group, we're working a lot in the lithium sulfur batteries. So people who might want to pick up some interest in that, I'll be glad to hear from you. Surface geochemistry is a cross-cutting team within my team where we apply most of all this knowledge to mineral separation, mineral processing, and to all geochemical reactions that take place in nature. So it's quite broad, and further interactions can be picked from with the group website, where our primary goal is understanding structure, property, performance, relationships in solid-state material. So the goal is when we take a particular structure, what are the properties that can be inherent, particularly to that structure, and how do those properties affect the performance of the structure that we are interested in? And those are things that we want to unravel from an atomistic point of view. So just to dive into the theme of today, we look at the global energy challenge. It's something that we are all facing. It's something that everybody needs to make a contribution to. So as you see from here, that the world energy demand is projected to double by 2050. And that will mean a massive thing. If right now what we have is insufficient to sustain us, if it's going to double by, our demands will double by 2050, and even triple by the end of the century, it means that we also have to radically be doing something to catch up, or else we will be left behind, and the consequences of that may be there. So one of the daunting challenges that we face today as a society is to generate sufficient supply of clean energy. It's not just energy, we're talking about clean energy these days, and that is a key thing that we are all striving to see how our contributions will be. The reason why we're looking at clean energy these days is because we all agree and we all understand that the guy who has been serving us so well, everybody kind of trying to pick up on him now, which is the fossil fuel. They continue to serve us, but we know that there are challenges with them with regards to environmental concerns. And therefore, the key thing that as we burn more fossil fuels, we release a lot of CO2 into the atmosphere. And generally, this will accumulatively sum up to increase temperature. And therefore, we see negative consequences. And a lot of them we see in all kinds of places. And typically, this is even happening to the more impoverished places where they suffer severely from the catastrophes of climate change. And that is why that bell is banging and banging these days. Everybody wants to make some contribution in that area. So this quote I want to say here, that Gutierrez, the UN Secretary General, currently said, okay, because of all these things, then can we stop burning the planet and start investing in all the renewable energy that is around us? I will always want to say this cautiously, that fossil fuel is continuing to be part of our life, and it will still continue to serve us for a while. It means that we can't just stop away from them today. I have this proverb in my language, but that you don't bite the finger that feed you. So fossil fuel has fed us all this year. We don't just bite it off. If you jump out too early, it will lead to problems. So fossil fuel is still going to be part of our life. The goal rather should be then, as he put it, that we need to start investing in green energy technologies. The key thing is that as we invest more and more and more, our dependence on the fossil fuel can decrease alongside the journey. So that is very important. But as we look at it, that it means that we need to move to greener mix. And the greener mix, actually, we're looking at the photovoltaics, the wind, and we're looking at hydrogen productions. These are what we're calling the greener mix. And we have to invest in all these technologies in order to decrease our reliance on fossil fuel as we want to move away from them. So the goal is to innovate towards zero emissions. It's a goal. We have to keep innovating. We have to develop more efficient, more robust system that will be able to innovate us towards that zero emission we are interested in. If we can do all of that and amplify the growth of the green technology, we will see that Renewable can contribute over 65% of green energy by 2030, and that could even double to 90% by 2050. But that will take a massive investment and massive research inputs as well. But I always put this that being green is not always easy. It's always a challenge. It's never easy being green. And therefore, it means that there's going to require a lot of effort from every individual before we can turn our planet green. And that's the goal that I'm here also to play my part. And I'm sure people are playing their part in every respective discipline that they are. So when we look at a sustainable energy future, the key goal is that, okay, yeah, now we look at a lot of CO2 produced from our power plants. But this CO2 can be used as a feedstock also, where we use photochemistry and electrochemistry to drive the conversion of these as well. We can produce what we call value-added chemicals. It means that what is a deviant cannot be turned into something useful as well. So our goal is that, yeah, in catalysis, that's a lot of work going on in that area. And we will need people to develop new robust catalysts that will be able to take all these raw materials, nitrogen, CO2, hydrogen, H2O, and produce a lot of value-added chemicals from them. We can produce hydrogen, which is also touted to be one of the green economies, from water splitting. And we need a lot of good catalysts that will be able to spontaneously do that. Our goal is that when we can do that, as we generate more hydrogen, we need to think about how to store them. So that's why battery development these days is also a very big thing within the agenda of the energy transition. We have to develop more stable, robust batteries to be able to take care of all of those things. And for sure, the photovoltaic switch, we know that has a natural abundance for us, and we want to tap into it. But it will not just happen by itself. We have to do something to be able to get it. So at the center of all these things is materials driven. All those green renewable technology is, so the rational breakthrough cannot take place if we don't have breakthroughs in material science. For you to have more efficient photocatalysts, more efficient solar cells, robust, strong turbines, we need materials-driven processes to be able to tailor all of those things. So at the center of all this is materials and minerals. And the reason why minerals comes in is that we're looking at batteries. Most of these batteries are based on cobalt and nickel within them. And therefore, we need to find out how minerals will play a role. That's why these days, even within the green transition, we have what we call critical minerals now. Those critical minerals are going to play a significant role. And therefore, this will be the key thing that we have to go. I will be more focused on that, on the photovoltaics today. So we know already photovoltaics will give us a lot of economic benefits, societal benefits, just because we can get it from a super abundant resource. So the sun is always shining. Whether we tap it or not, it's always going to shine. The goal is to find materials that will be able to harness some of that energy and turn them into useful energy for us. So the US actually set this ambitious goal to have a carbon-free economy power sector by 2035. That's a very ambitious one. And we have to understand that, and even want that to decrease CO2 emission by 52% by 2030. But you realize that to achieve this, it means that this goal, we have to deploy significant amount of renewable energy for us to be able to change that, drastically decrease our dependence on fossil fuel, or else the carbon-free will just be a dream and not a reality. And that's why you see government efforts now, the Biden administration, a lot of interjections of funds into the green economy to transition us towards achieving that goal. So for us to be able to do that, photovoltaics, which is going to be the key driver within the renewable technologies, has to really double as well. It means that the way we deploy solar panels these days has to increase significantly. And if it has to increase significantly, we need to start thinking of ourselves, what are the current ones that are in the market? So you will see that dominantly silicon dominates both of them, either from the monocrystalline or polycrystalline. That's already over 80%. So currently, all the solar panels we see out there on roofs and etc., majority of it is taken by the silicon. But the reason why silicon, human beings, we always want things to be flexible. So silicon is a braided material. We have to cut them from ingots. So generally, they are braided material, and therefore, and they also, silicon itself is an indirect GaN material. So it means we need thick materials to make them. So that's why cost will be higher. It's a very difficult material to process as well, high temperature processes to process monocrystalline silicon. So that would mean that the energy input is very high, and that is why cost will still be quite high for it. So the goal then is the one who is contributing less now, can we drive that also for the thin film solar cells? The reason why thin film solar cells needs to be driven up to catch up with silicon these days is because of the following. So in silicon, typically when it takes silicon, we want material thickness of about 200 micron. That's thick. But in thin film solar cells, we can drastically reduce the material input by just 1 to 2 microns. That's a significant drop. So what then you achieve is that the material input into making those devices will significantly drop, and therefore there's a potential to decrease cost as well significantly. And that's why thin film solar cells are very, very important processes that we want. The thermal budget for them equally is very low. We can make most of these things at much, much lower temperatures. So the input you have to go into them will also save you cost. Generally, they tend to have lower efficiency, but these days, a lot of them are showing massive increment in efficiency, and I'll discuss some of them. So when we talk about thin film solar cells, basically we're looking at using an absorber material that is within the micron thickness compared to 200, 300 of silicon. And the reason why we like it is because it's a flexible material. These days, human beings, we want aesthetic beauties in every area. We want to integrate them into our building. We want to develop more efficient buildings. So solar panels are now integrated into buildings. Instead of using concrete and bricks, panels are replacing all of that just to even give it aesthetic beauty as well as save cost and make those buildings more energy efficient. They're very flexible these days. We want to try things on the go. So textures and flexibilities are there for us when we go for the thin film solar cells. Another beautiful thing about the thin film is that they can be fitted onto any substrate, be it glass, aluminum, polymers, etc. You can just lay them off your roof like that and start generating energy. So they're very flexible with light. We can just paste them over onto any substrate compared to silicon, which you have to know that it's a rigid material. So if it is a curved structure, you aren't going to get that silicon onto it because silicon, if you want to burn it, it's going to break. It's a brittle material. So currently in the market, you see amorphous silicon, cadmium telluride, and CIGS as the three dominant advanced already thin film technologies out there. Most of them are achieving very good efficiencies. Silicon, most of them you can see efficiencies are between 8 to 14%. Cadmium telluride is doing amazingly well and it's been robustly integrated into a lot of photovoltaic systems already, 22% efficiencies that they are already clocking. The key question that comes into case is that tellurium is a scarce material, very scarce. And therefore, when you talk about scalability and large production, that is going to be brought into question. How much can we produce, considering that there's a tellurium in it? Cadmium itself has a lot of question mark because of toxicity issues. It may leak out into our water bodies and make life difficult for us. Yes?
Nice. What is the efficiency of the standard thicker solar cells?
Okay. So
just to complete, so
yeah, so when we go to the monocrystalline silicon cells, most of them are also achieving over 20% efficiency already, 25, 22, 24% from the monocrystalline silicon. So in the thin films, what happens is that this percentage drop when you use amorphous silicon, which is again a silicon-based product, but it's an amorphous one in a thin film form, and those are less efficient. So you have 18 to 14% within those ones. But you can see already that some of the other thin films like cadmium telluride already catching up, doing amazingly well compared to even a monocrystalline silicon already clocking over 22%. And the same way, if you look at the CIGS, you can see high efficiency, even 23.4% efficiencies in them. The CIGs are typically popular in Europe and in Japan. They have invested heavily in this technology and have deployed them in large scales as well. But you can see here that there's again question mark of indium and gallium, which are also critical material. They are rare, it is scarce material. So the question is this something that we can scale up? If now some other areas can take it, but if we want to talk about global scale mass production, where do we get indium? Where do we get, there's competition even for India for the screens of our phones, for our televisions. So there's a lot of competition for it. And the question is, if we want to go for it, where do we get them from? And that's the key question, why we need to think of something else. So one hot material that's coming to the market these days is called the perovskite solar cell materials. They have been in the around for just about 10 years, a decade, but have done extremely well in terms of efficiency and how robust they are. So you can see that just around 2000 efficiencies were low, but now we can produce them even at 25% efficiency in perovskite solar cell. If we take them in conjunction with silicon, it forms tandem solar cells. We can even drive the efficiency to almost 30%. So this material is a very, if we talk about solar cells now, they're very hot. They are in hot demand, literally, in the market, but they have a lot of question marks. So they're doing so well in the lab scale. But the question is that they have all these hurdles. And that's why material science is still necessary to intervene to drive this forward. So the hurdles we see about them is that their material is doing so well, so robust in the lab scale. But the key question is that it is highly unstable material. So it can easily degrade in the presence of moisture, light, and oxygen. And we know these are the natural conditions. When we make them in the lab, we need to send them into the environment where the harsher conditions of life will treat them. The rain will fall on them. The sun will shine on them. All kinds of things will happen to them. So if they're degrading under those conditions, it means that we need to go back to the drawing board and do something to stabilize them, to make them more robust, more stable before. If we can do that, yeah, they have a lot of wide range application because In terms of efficiency, they are doing amazingly well. Our goal now is to stabilize them. And the questions then comes to where? Where is these deficiencies coming from? What is really driving them? Why are they breaking down so easily? What is the question mark about them? And that brings me to the quote which formed the part of our topic today as well. This was quoted back by Kumar in 2020 when he was giving his Nobel Prize for physics in that year. He said, the interface is the device. That was in 2000. The interface is the device. And then he was actually looking at other remarkable properties that we can attain when we bring two things together. And the question is that statement still hold today? Yes, it still holds today, that the interface is still the device. So that was 2000, over 20 years ago, and the goal is to let us know why the interface is still the device. And that's our goal today. So all the renewable energy technology we talk about, be it solar cell, be it solid state batteries, be it a photocatalytic system, most of these materials are not based on just one material. They are based on materials being coupled together. So they form a lot of interfaces. You bring one material to the next one, to the next one, the next one. You need synergy between those materials, or else you aren't going to get anything good out of them. So that is why interfaces in solar cells is just basically have here a wide range of material deposited on top of one material. So you can have this active material here, which is so good, but if everything goes wrong at the interface between all the other layers, terrible efficiency you will get from your device. The same way, if you fabricate your batteries, you have all kinds of interfaces within the material. There's a metal electrode, there's the solid electrolyte, there's an interface between that and that. And you want to make sure that all these interfaces are optimized. They have to be in synergy, or else the performance of everything will go down significantly. The same way in catalysis, we want to drive all these reactions towards electrons and holes. If you have interfacial phenomena, you can't drive all these electrons across the interface. Where do you get electrons to do your oxidation and reduction reactions? That's not going to happen. So interfaces, that's why I still call them that. They're still the device, and we really have to understand them significantly. Why are they significant in solar cell? Practically, in solar cell, the reason why we're interested in them is because they control what we call the charge carrier dynamics, the carrier dynamics. So your absorber material is there, which is somewhere there. But what we do is that we have to now put another material. When I excite the electron, I need to be able to collect those electrons. If I'm not able to collect the electrons, I don't produce any electricity. So it means that you can excite electron, but if your electron fall back, which we call recombination, then you get no electricity. So that is the reason why we have all kinds of material we call the buffer material, and other people, we call them the whole transport material, the electron transport material. Those are materials you deposit on the material that you are interested in, so that when you excite the electron, you can collect them. Another one to pick the hole, so that they move them in opposite direction to minimize their recombination. So our goal, therefore, is that when you have a material system that the interface is terrible, basically what we come here, we call something called trap states. So you deposit this material on top of the next material. If the interface between them is not in synchrony, what happens is that there'll be defects in that interface. So you excite the electron, but what happens is that the defect will trap the electron. They will just hold on to them. They don't send them for you to collect them. So what happens is that you never get any good efficiency. More can be generated, but more will be trapped. So we want to make sure that there are no interfacial trap states within the interfacial region when you form those. And again, also because you deposit another material on top of the next material, you want to make sure that the barrier those electrons and holes who have to cross is not too high for them. Or else, if the barrier is sidebar, they have to cross over to the next material. If the barrier is too high, they will not be able to cross over to it. So we also want to make sure what we call the band offset. So I have here an electron is here, it needs to be able to jump to here for me to collect. If this well is too deep, it's just like you put me in a well. I jump, but I can't cross. I jump, I can't cross. You fall back. Where do you go now? You go back to where you came from. You recombine. So if you have a system such that that barrier is too high, what happens is that you can excite as much electron as you want, but none will ever get collected. They will all fall back to recombine. You get nothing good out of that device. So we want to make sure that our interfacial band offset, the barrier that electrons and holes has to overcome, it's something that we want to control. And interfacial phenomena is the key thing. So we have here a typical solar cell device from a perovskite system. You have here this region. So you excite electron. You want to make sure you collect the electron through here and the holes through this, or the electrons are going through the electron transport layer, the holes through that. What happens is that if this interface here, which is connecting this material and this material is bad, these electrons can get there, but once they reach the interface hold it onto it. It doesn't release it to go. So you never get them collected. And it's all this that we want to control now. So you excite electrons, but you want to make sure that you collect them down. And all these barriers, every step you see is a barrier. We want to make sure those barriers are not too extremely high for them, so that you don't get them collected. So the key thing is that the synergy between all the layers within the material, particularly between the absorber and the electron transport and the hole transport, has to be in good synchrony, or else you aren't going to be able to get anything good out of that device. So different types of alignment can happen. So I bring one material on top of the next material. What we want to achieve is there are different types of alignment. One is called type 1. I won't bother you too much. But the key thing we want to say here is that if you partner this absorber material with electron transport layer, you want to make sure that these electrons here can come down. Now watch this one. If this form a type 1 alignment, here the electron will have to jump. Which one do you think will help you collect the electron more? It's going to be the one that they are descending, free fall. So here, the offset here is negative. It's just come down. They don't have to jump. Here, they have to jump. There's a barrier. So there's a positive band offset. So again, that is what typically in solar cells, type 2 band alignment is the most preferred because the electrons can do a free fall. And it's so easy, like thermodynamics will tell you, that on a hill, if you release a ball, it will naturally roll down. But for you to roll that ball back to the top of the mountain, you got to give it energy. It's not going to happen by itself spontaneously. So typically, those are all the things that are happening at atomic scale we see in our solar cell systems as well. So the key thing is, how do we also predict those band alignments so that we want to know what is the offset, what is the other offset, so that we'll be able to engineer them. Is it too high? Can we do something to decrease them? And that's the key thing that we are interested in. So a lot of those properties will happen. Now, if I take one material and the next material, I bring them together. This is what you call the electrostatic potential. So they will have an electron redistribution among them. Now, this electrostatic potential can change, especially at the interface region. You see that this is coming, but when you reach the interfacial region where the bonds are forming between one material and the next material, that is where things may go wrong. So we want to understand what is the behavior of that interfacial region so that we are able to use it to predict proper band alignment within the material as well. And that's the key thing that we drive, and we want to employ robust computation to unravel. So the interfacial effects, this most time you see a lot of predictions will base on just the bulk properties. We call them ionization potential, but there is an interfacial effect, which when you neglect, it will poorly determine those properties of the material. So defects are, as I said, defects are things that we can't run away from in materials. Defect simply means either there's a vacancy, there is an interstitial within the material, and generally most material, because we sensitize them under different conditions, sometimes you have defects within the material. So you may have a material that has a vacancy, one atom is missing in the lattice, or you have another impurity within the material. All those impurities can have different effects on the system that you have. Some may be bad, some may be good. More often, they are bad. So our goal is to make sure that we control defects within these materials as well. So if there is defect within the material, what they typically do is that they also trap your electrons. And what happens is that your solar cell efficiency will drop. So our goal is to always control. And these defects are even more pronounced in the surfaces of the material, not in the bulk. So in the surfaces, that because you've already cut some bonds, a surface simply means you cleave the material. So once you cleave materials, what happens is that the topmost atoms will have lost some atoms because you cleave their bond. And they are the ones that easily will lose atoms now because those atoms don't have all their full coordination. They can easily become a vacancy. So all kinds of things can replace them. So the surface is where things actually even go wrong. And now if that interface surface is going wrong and you couple that with another surface to form an interface, if something is wrong with this one, something is wrong with the other one, you bring the two together, all you can get may be wrong. That's why there's a defect, massive defect within the interface region. And that is where all your electrons may get trapped. So we want to make sure we understand that very well. So the goal is, can we engineer surfaces of material? The goal is this, yes, if we can tune the band alignment, just as I've told you, to make sure that those barriers or resistances are not too high for you to collect that. Third, carrier dynamics. We want to make sure that when we excite the electrons, we are able to collect them. That process, how can we efficiently improve them? Generally, when you have defects on the surfaces because of dangling bonds and because of missing atoms, what we do, again, as an engineering point, is to passivate the surface. Passivation simply means you introduce another organic molecule or anything that will coordinate to that bond so that when the electron get there, they don't have that spot to be held in onto. So you passivate the surface. And typically at the interface region, there can be diffusion between the two materials. So one material from one can diffuse into the other. We want to minimize that as well so that there's no interdiffusion when they come to the interfacial region. And all the barrier function, typically, as we said already, water may be exposed, oxygen may be exposed to this material. Those can lead to all kinds of barriers that we want to make sure we circumvent. If we can do all this very well, which we call interface engineering, by doing something to align this properly, we can drive our efficiencies forward. We can also improve stability of our devices. And that's how we can drive all these new emerging materials towards commercialization. Until we can, efficiency is so good, but if our stability is terrible, we're still not going to go here. We can only commercialize when we have both of them working in unison. So passivation simply means this. So if you cut this material, have this top atom, that can be a trap state because there's nothing coordinating to it. But if you passivate it, you bring another molecule, you can hold on to that, and the electrons will still flow through the material, not using this as a spot to fill. Because every time you lose coordination, I always call it you are unstable. I use this example for people, like you are in the water, you're getting drowned. Typically, when somebody comes to save you, if that person is not a good swimmer and doesn't know how to save people, the drowning person will hold on to you. And both of you may end up dying. Because that person can see death. He will cling onto you seriously. And you can't swim anymore. You can't save the person anymore. Both of you will go. And that is the reason why anytime you have instabilities in material, it means that this bond here is not comfortable. It wants to have more bond to it. So if an electron comes, it will hold the electron and do not want to release it. And that's what we want to control by passivating the surface so that those spots are not there for those electrons to say, I want to clinch onto. We want you to flow through so we can collect you. That's the goal. So you can see a lot of work going on these days where people are passivating surfaces, all kinds of organic molecules, and you can see efficiencies are being driven. So here they have a control experiment that gave them efficiency of 11%, but you can drive that to 14.75% by just introducing these passivating materials. So basically they make this material, they passivate them. So this is the perovskite itself. You can see on the next one, they deposit a layer of those passivation layers. Those will stabilize those defects. They will remove all those dangling bonds, and therefore your efficiency will go up, as you can see here. And you see that happen in even other devices. You can see here efficiency was driven to 23%. Again, just by nano-engineering the surface of that material. So these are exciting things that are happening within the engineering community of material science, where we want to engineer surfaces of material and make sure that we can drive these efficiencies as well as stability in the upward direction. Cadmium telluride has been part of our life, but you can see here recent a paper that was in 2018. Most often we see efficiency of 22. By just engineering the interface of that material, efficiency could even be shot up to 25%. What did they do there? Basically, what they replaced was this. So this place was having what we call cadmium sulfide as the buffer material, which was collecting the electron. They just introduced a new material called magnesium doped zinc oxide, and that tailored the band offset properly, lowered the resistance, more electrons can be collected, efficiency shoot up from 22 to 25%. That's engineering. So you understand what is happening in the interface, and now you know that, oh, this is the header. This is the bottleneck. Can we control that? What can we do to it in order to make change those things in the direction we want them to be? That's basically what I meant by the engineering. So when we do that more often, what we want to make sure we understand is that a holistic approach will be needed. You can do this understanding of those interfaces with only experiment. You need a synergy with computation. So molecular modeling comes into, so when you have a marriage between theory and experiment, a lot of beautiful things can happen. Where the two meet, the things that experiment alone cannot understand, modeling can unravel those parts. The part that modeling cannot unravel, experiment will unravel. And the two working together gives us a bigger picture of the problem and how to holistically address it. And that is why I am a strong proponent and advocate for using computation and experiment working hand in hand together. And the reason why computation is so important these days is because we really want to drive technologies forward at a faster rate now. Human rate, the challenges we face today are not challenges that we want to be slow marking time. We want things done. It takes silicon from 1954 over 30, 40 years before we could take efficiencies over 20%. It started off efficiency of 6% from silicon. After 30, 40 years before we drove them beyond 20. The question is, if we want to deploy renewables in the next 10, 20 years, do we have to wait for 40 years before we can drive the new technologies forward? No. How we can speed up that process is when we do the combination of both of them. Employing the robustness of computation, artificial intelligence, machine learning, to diagnose materials problems so that we can synthesize them at a faster rate. Instead of going to the lab and doing try and error experiment, we can explore those material configurational space using computation, and that will speed up the time at which we can even go ahead and make those materials. So it's a very important thing that we reduce all these barriers, and when we do theory in combination of that, we can drive everything almost by 10 times faster. So if it takes us 50 years to do that, maybe we could do that in the next 5 years. So that's how technology driven, if we can combine both of them in good marriage, working together well. So there are different lab scales we look at, but anything that's going to happen at the large scale, the macro scale, will be driven by the electronic and atomistic. All these are electron processes. They happen at the atomic scale. So we want to know what is happening at the atomic scale of this material. And the key thing there is, how do we understand what is happening there? So different approaches have been employed. I won't go too much into the technical details, but I just want to point out that we have reached a stage in modeling where we have huge computer processing power to us now, that we can really simulate a wide range of systems, depending on what you're interested in. If you don't care about the electrons within the system, but just using classical bodies to see how will this atom connect with this atom, these are what we call molecular mechanics. We could simulate a wide range of this. This is just the Lennard-Jones potential. And again, a robust model that was developed in the 18th to 19th century, but this is still relevant in today's time. We could use them to simulate all range of problems. So here, this is like things like radiation damage, crystallography, protein folding. We're talking about billions of atoms. The question is, can we model them? There you can consider the electrons, but there you can consider only the atomic configurations. This day we want to predict protein folding, DNA structures, etc. Those are all things that those type of modeling will give you. We don't care about electrons, so we can simulate a significant large number of them just based on molecular mechanics. But the part that is of interest in the renewable energy technology, electrons are going to be key players. You can't throw away the electrons. If a photon strike a solar panel, it generates electron hole pairs. If you model that process and you say, I don't care about the electrons, you are not describing the system. So different type of modeling has to come in, and that's what we call the quantum mechanics. So quantum mechanical approaches are what we use to solve those problems. This equation here, it looks very simple, very, very trivial. But to try to solve that problem, even the biggest supercomputer in the world doesn't really give us a clue, just even beyond one electron system. So a lot of approximations has to happen in order for us to solve that simple equation we see there, called the Schrödinger equation. So what do? The breakthrough came in sometime in 1954 when Kohn, this guy here, he won a Nobel Prize for chemistry, I think in 2010 or 2009. And what he did was basically to simplify the problem. He said, okay, if you take an ion, you have a lot of many-body electrons around it. Can we now say, oh, let's treat all these electrons as a cloud of electron, density of electron. As soon as you do that, what you reduce is that you reduce the problem from a many-body dimensional problem to just three-dimensional problem. And that is not tractable for most computers to solve. And that is why it has revolutionized the materials modeling community and has been used extensively to understand and design new materials. And these days, you can see that because now of that, we can now screen what we call high throughput material. We can design new materials, predict different new material. And this is what we call high throughput simply means now we have a wide range of databases for material science now. But high throughput simply means I want this property. I take the bigger funnel, let me throw all the material in. Which of them will meet the targets should go through. If you don't mix the target, you come out. So we can use the funnel approach to screen the best possible materials for different applications. Here, I'm just looking at solar cell, but this has been done extensively for catalysis for all kinds of applications as well. Machine learning is picking up significantly in the area where we want to say, we have all these data available to us. Can we derive correlations and trend in the material so that we know when this chemical is missing with this chemical, these are typical properties that come, correlation effect. So we can design new materials at a faster rate. And that's what machine learning is also helping us to do. So typically when we talk about machine learning, basically we have a lot of data. We want to make sure we train that data, and that data can give us new prediction. Based on those new predictions, we can look at applications of them. So there's a lot of things going on in that area, and that's an area going on within the materials community now called machine learning and artificial intelligence. But as I give you some few snapshots of what is going on in the areas I want to highlight for you guys, when we talk about solar cell, there's something called the golden triangle of PV system, the golden triangle. So there are three things that drive there. We have the cost that is of interest to us. Everybody cares about cost. Why something is too expensive, you don't want to buy it, right? So we want to make sure that we drop the cost of our solar panels significantly. The next thing we care about is efficiency. Everybody wants to buy the most efficient solar panel. If you buy the less efficient one, it means you have to buy more of it to achieve the same result for your property or building. But we also care about a lifetime. I want to make sure that I buy the solar panel, it doesn't break down tomorrow or break down after 1 year. Typically, the crystalline silicons, we want to look at over 20 years. We want to use them as significantly as possible. So this becomes the challenge we all face. A material may be so efficient, but the lifetime is so terrible. It may be so cheap, but maybe it doesn't give us the efficiency we want. So we're juggling with all this. It's a three puzzle we are fixing, trying to optimize all three parameters at the same time. The question is, who is going to win? And it's something that's still going on. We look at perovskite, we see that already coupling them with silicon already is almost 30% efficient. So the efficiency is no problem. Amazingly good. What of the stability, which you link to the lifetime? Terrible. The question then is, can we drive that forward? So these are all the puzzles we will be solving, and engineering is what we need to do them. So I just want to show you some highlights of some recent work we did on those three systems, these materials, which are all F-abundant materials. We call zinc phosphide, pyrite, and perovskite, which I've worked on recently with a number of people across the world. I just want to give you some highlights of them. So one of the material that I have been very, very interested during my time in Cardiff, I spent a couple of time working on this material with a wide range of experimental colleagues, is called zinc phosphide. This material here is what I'm comparing all the other properties to the other ones. So silicon is here, gallium arsenide, CIG, the perovskite. Here, the reason why this material is so exciting is that it's a direct band gap material. You can see its band gap is about 1.5, which is typically, when we're looking at solar panels, we're looking at materials that have typical band gaps of 1 to 1.5. Those are the ones that give us the best efficiencies. Silicon, for some reason, has a very low band gap of 1.1. It shouldn't have been the best absorber because it's even indirect band gap material. But for some reason, it's the one that is serving us so well. It's just we have figured out, it has been with us for a very long time. So we have figured out how to make it work. The thing is that all these guys are also working, but we have to figure out how to make them even work better. That's the goal. So this material ticks all the boxes of things that one may want to consider when we want to produce solar panels. And therefore, the key goal is to combine modeling again with experimental synthesis. We want to make this material, we want to investigate what are the properties of defect chemistries, interfacial phenomena in this material. Our goal is to drive efficiencies of them. Presently, they are operating around 4 to 6%. But there's room. Silicon started with 5.4. If today we have 25, 26%, there's hope. And that's the goal. We want to drive this forward. But we have to think about what are the things that may go wrong with this material. So typically, when you have material surfaces, we have to send these in under environmental conditions where there's water, there is oxygen in the environment, the harsher conditions they will face when they go out there. The question is, how will water interact with this system? How will oxygen react with this system? If it reacts, does it change something that we need to be conscious about as we make devices from them? So we set out quickly to unravel the oxidation chemistry of this material. And how do we protect them? Protecting simply means to passivate the surface. You introduce functional ligands that will couple the surface and protect it for you. So there was a paper I published sometime. This was a single other publication during my time in Cardiff, where we look at to set out how does oxygen react with this and how does water also react with it. The interesting thing, which is just a highlight, is to tell you that typically all these species react very strongly with their material surfaces. They're binding so strongly with it. And not only are they binding, but when they bind, they pull a lot of electrons from the material surface. So there's a lot of oxidation happening on the surface of the material. Now, you will see the effect that when water also reacts, you see water binds not as strong as oxygen. So first of all, already you will know who is going to be the main deviant. If it comes to deteriorating the device, it may be that the oxygen binding too strong may do something bad to the device because it's oxidizing the surface of that. The same way, when water binds, water can split. So it forms OH radicals and hydrogens on the surface. All those things will determine the surface chemistry of the material and therefore change the properties of the material. And you will see here, interestingly, when we did the electronic properties of that, we learned definitely for sure that when you introduce those species, they begin to decrease the band gap of the material. So they shrink the band gap of the material and introduce what we call defect states in the material. So it means that if you don't do anything and you just use that material to make a device and you send them in the harsher conditions where they'll be exposed to oxygen and water, you may start off at the efficiency of 30%, but maybe after 2 days of use, when the rain falls, the wind blows over it, the efficiency drops sharply. Just because you've forgotten to know that, oh, those things have negative impact on the material. So sometimes what we then do is that solar cells, these days we think about encapsulating them. We want to protect them. Sometimes when we synthesize them, we passivate the surface. So we went further to solve that problem. So we know there's a problem. How do we solve them? Passivation. So we introduced this one of the key pacifiers used in synthesizing nanoparticles and thin films of this material. So the question is, how do they react with the surface? What do they do to the surface? If truly they have to protect the surface, we want to know how does it first interact and how will they protect the function that we want. So this molecule here, as you see here, has 3 ligands. We have the thiol group, the amine group, and the benzene ring for it. All of them will have different reactivity depending on how they bind to the surface of the material. So that's something we set out to unravel, and we look at them at different surfaces. But the take-home message for sure is that the sulfur guy, the thiol end of that material, is what is going to dictate the binding to the surface. That's the one that will bind, anchor itself to the thin film surfaces. And the most important thing is that when they bind, the charge transfer between them is very negligible compared to the oxygen and compared to the water. So it means that they are not really destroying the electronics of the material. And beautifully also, when you look at the band gap before and after you cap them, you realize that you don't lose the electronic property. So they protect the electronic property of the material for you, which is exciting. And therefore, our experimental colleagues could pick up this work now. So I have a collaboration with a group in EPFL in Switzerland, who we collaborate on that. And these materials are now things we are developing. So they find a robust way to now make this material under the given conditions that the models are predicted. So we can synthesize these materials now into all kinds of nanoforms and nanoships into different thicknesses and characterize them extensively. This was one of them we recently published. And then also we could now make this material. So during the synthesis, they discovered that, oh, one growth phase can be that you have a thin film, but then there's a rotation on the surface. So the same surface, but then it rotates over the other. What does that mean? Does it mean when you now form an interface because there's a rotation between the base and what is on top, how does that change? Is it destructive? So they quickly contacted and said, Nelson, this is what we're observing. Do you think that's going to, the film we produce is still going to be good for solar cell, or it's not going to be good just because of those domains we have formed, which are rotated domains? So we can explore that and model those interfaces explicitly, and then also determine the electronics of the interface. And the key thing you will learn from them is that within the gap region, which you call the band gap, there's no interfacial effect. It means that even though they form there, and the reason why that will happen is that it means there is synergy between the rotated domain and the substrate. So that doesn't destroy that. And that became a very exciting result for them. And those thin films are already currently being used to actually fabricate the solar cell. It means that you have domains which will also be good for carrier transfer. So this particular beautiful piece of work, which I will talk briefly about, it's a system that we did some time ago, just to tell you the power again of modeling. Some things that we believe to work through maybe in the 80s and 90s may not necessarily always be true, just because the techniques we used to characterize them as at that time were not as sophisticated as the techniques we have today. So, but if we don't revisit those problems, we might be misleading ourselves, thinking that that thing is a bad thing. So this material pyrite has been of interest for solar cells as well, but it always comes along when they make it with its sister we call the marcasite. So it's a polymorph of the other. And this polymorph, in the 1980s, this was the band gap somebody predicted using electric measurements. They say the band gap is 0.34. Pyrite has a band gap of 1. So the goal is that when you put this into this one, the band gap will shrink. It will shrink your band gap. But the question is that true or not? So I revisited that problem some time back. We modeled this system, and the key thing you can figure out there quickly is that the band gap of what was thought to be much, much lesser is actually turned out not to be true. So by just revisiting the problem, we can see the band gap of that is now more than even the pyrite itself. So it means that when you engineer this material such that you form proper interfaces, it should rather be beneficial, not detrimental. And that just around the same time we published this work, this problem was revisited by spectroscopy, more advanced techniques, and they also actually predicted the band gap to be just about 1.something%, which was far higher than what initially was thought of to be 0.34, and has been cited over 40,000, 50,000 times as the main deviant. So we could model how actually will those interfaces form with the material. So these are all things we could model, determine morphologies of nanoparticles based on the surface energetics, how stability of those surfaces are. You can see here, this is something that is synthesized. This is what is modeled. You can see this morphology here is just exact as predicted from the model. So modeling these days gives us a lot of power to really unravel even systems before we go ahead and make them. So we could study these surfaces of this material and then use further. So this is the pyrite, this is the marcasite. Now, when you bring them together, what kind of interface will they form? Because now they're going to form domains. And we can model this is the interfacial phenomena in this material. And the beautiful thing is that if you watch the microscopic electrostatic potential, at the interfacial region, there's no jump. It's just the red line here. It's just continuous and smooth. What that tells us is that they form a very perfect interface with each other. And because they form a perfect interface with each other, that should be beneficial. Assuming that interface there is defect in it, you will see a sudden jump. There are some dangling bronze, there are some vacancies, you will see a sudden jump. And that will be detrimental. It means when the electron reach the interface there, those guys will hold it. And then you can do what we call the band alignment with a system. Basically, what we end up learning is that when you form interface between the pyrite and the marcasite, your electrons will flow to the pyrite phase, and this will flow to the marcasite phase. So this is a type 2 type of alignment. You can see here it's going to be a free fall. The electrons will just fall. They don't have barrier. They don't need to jump. They just fall down. Thermodynamics tells them that they should enjoy it. And therefore, those electrons can then be connected to a metal, and we color the electrons and drive electricity. So this can be made as well experimentally. And the key thing they learned from this is that just by forming the interfacial with this material, your photocurrent, the current density that you can generate astronomically went so high compared to just if you have the green, which is so low. So the single phase material, it means that if it's single phase, you can send the electron up, but the electron can fall down. But if you partner with it, when you send the electron up, the electron will flow to the other one, so it doesn't recombine. And that is why your photocurrent can be significantly improved. And the last thing I will touch base on is some new system we really work on. We call the inorganic perovskites. Amazingly, they're making a lot of headways these days. Efficiencies are already just about 20% in these systems. Basically, what we do in the perovskite is that this central atom here can be an organic cation, or can also be just an inorganic cation. The ones that are doing so well in the market now are based when you substitute the organic cations. But the problem with organic cations is that they are the ones that introduce a lot of the defects. So the goal is, can we move away from the organic cations and introduce what we call the inorganic cations? And that's why we're designing what we call all inorganic cations. This will help you improve the stability as well, because organics will not necessarily evaporate, they will not easily break down, and therefore your material won't just decompose as we see in those materials. They are so efficient, but they easily break down. So the goal then is to replace those organics with an inorganic system. And this work we did with a group in South Korea in Chonam University. Basically, one of the key things I want to highlight on this is that this is active absorber material. But so this is this one here. What we then did actually was to say, okay, what if we passivate the surface of this material by introducing quantum dots of the same material? So typically, when you synthesize the material, it's a topmost layer, as I said. There may be defects, maybe other things, but we can passivate that. We can fill in all the vacancies so that there are no trap spots. So we need to now deposit something that can fill all those spaces such that electrons can naturally just flow through the material. And this we did actually, and it turned out to be one of the amazing pieces of work. In your control experiment, just for that device, you see that 10% is what you achieve. But just by passivating the surface of that material, we drive the efficiency to 17.51%. And these are things that we can unravel from modeling as well to understand what is actually happening when you even introduce the key element we call terbium, which we dope into this material. How does it change the electronics of the material? And those are all things that we are really unraveling and combining with experiment to understand why the device is going to work a particular way or not work a particular way. And lastly, we take this work further and say now, so we saw this piece of paper, very nice, decent work where they now form heterojunction. So they synthesize the same material, but now they form a heterojunction by doping in an organic molecule again. And the thing is that organic guys, because they easily break down, the question, we want to stay with all inorganic. So what we then did is that, what if we have polymorph of this material? It can come in the beta phase and gamma phase. Because similar to the pyrite marcasite work we did, so the material stay as this. Can we rather form the retrojunction between those ones so that the material still stay as purely inorganic? So that what this group did from San et al., they still introduced an organic molecule. So we model the interface of this material, passivated it. You can see beautiful stoichiometries of the nanoparticles of this material. No the defect chemistries with this material, just because we have formed now the heterojunction. So this here is what we model from computation to know that the interface is very, very uniform. And you will see that once you do that, what did we end up achieving? This is currently the highest efficiency for all inorganic solar cell. This work is currently under Nature. So there's a lot of technical details that I'm going to escape a little bit because we're still trying to get it through into Nature Energy. But the key thing is that the stability of this material as well, we can retain even the efficiency for a very long period of time of testing under ambient conditions of robustness of air, water, etc. So there's a lot of room that this engineering, just knowing what happens in the interface and engineering it, we can achieve a lot of beautiful things. And I will conclude this with this particular slide. That one piece of new things we are doing is actually now using machine learning to probe surfaces of this material. So instead of now I put one surface like this, we can rotate the surface and find out the most optimal configuration. And that's something that if you want to do by just purely compute either DFT, it may be time consuming. So machine learning now gives us the freedom to rotate what we do structure search I can put one material on top of the next, rotate it at all different possible, and find the energetics to know the stability of them. So one of the seed grants we recently had is probing into that. One of my students, Henry, is in the audience, is beginning to look at this material we call chalcogenous perovskite. It's another type of material, but it's highly stable chemically and thermally. And this was a grant PI in conjunction with Adri Van Dijk in mechanical and Ismaila in material science as well. So the take-home message I just want to give us today as we try to wrap up is that the interface is still the device. If there's anything you will have learned from here is that the interface is still the device. Until we have control, fair grip of it, control it, understand it, we can produce whatever device we want, but they won't give us what we want. So first is to know what it is and how do we tailor it to achieve what we want to do. And then I propose, therefore, that the marriage between experiment and modeling is the way to go, where we need to make sure that there is a harmony between computation and experimentation in order to understand problems with a bigger picture. What we can see with one eye, the other eye will see. And therefore, once we have that, we can do extremely well. And I also want to say that compared to bulk materials, we have a lot of databases for this material system. But interfaces, we don't have any database for them. So this is something that a community of engineers and surface scientists we need to start thinking about. Creating databases is something that I want to champion myself and I want to begin to work on so that we can say that we can create a repository where interfaces that are modeled concretely, we can have those data that can be tapped into. Machine learning can come in, pick those data, and even screen correlations. And that's something that is a work that we need to be driving forward. So that is the reason why this work is exciting, and interfacial scientists and all needs to come on board, and we can simulate that. So just want to thank a wide range of collaborators who have been involved in all aspects of the work. Thank my students, funding from when I was in the UK, the Royal Society, PSOC in the Netherlands as well, and now the department of my department as well as ICDS for seed funding. And I'll conclude by this statement that the real voyage of discovering is not seeking new lands, but seeking with new eyes. And that is where modeling comes in, to be the new eye to see what experiment may not be able to see.